Posso?
First.
Okay.
Good afternoon, good morning, and good evening. ACC Amarim Cork Composites is going live on the first webinar for the power industry. Welcome all. Today we have with us Rui Palavra, Global Technical Manager at Amarim Cork Composites, and we will be talking about noise reduction strategies, and in particular assessing the power of our noise and vibration design tool in reducing noise in power transformers. First of all, welcome everybody to this session. We are very pleased that we had so many people present in this webinar. Just to set the ground rules, we will start off with a recap on the vibration control basics, go through noise reduction strategies, and end up with the key calculations in the tool, which then can be downloaded. We will be monitoring the chat, so if you have any questions, please address them on the chat, and we have an end area which is designated for questions and answers, where Rui Palavra will be answering your questions on the tool, on other issues that you have that we can approach in the time that we have. The session will be 45 minutes long, and we are saving from 5 to 10 minutes for the questions and answers. So, welcome everybody, and we hope that it will be useful and that you will ask us to have more of these sessions. So, Rui, it's up to you. Please guide us through.
Thank you, João, for the presentation, and thank you all for attending this webinar. So, like João said, the agenda was divided in 3 parts. So we're gonna recap some VC basic concepts. We're gonna then talk about 4 noise reduction strategies, and we will end up doing some key calculations in vibration pad design on the NVD tool. Recapping the VC basics, transmissibility provides a measure of vibration control performance. And what you are seeing is a typical VC material curve for transmissibility. What we should see and what we should retain in this curve is that our materials exhibit a natural frequency below the disturbing frequency of the transformers. A natural frequency, even with thinner material like 10 millimeters, has a natural frequency of 40 Hertz or less. So below the disturbing frequency of the transformers.
Rui, can you just explain something? When you talk about transmissibility, what exactly do those numbers mean on the left-hand side of the curve?
Basically is the ratio of output to input, meaning if the values are below the line, the X, means that the material will isolate, so will be reducing the vibration in the transformer. So meaning we need to have the material curves below the line, where we see the line on 1. So meaning the lower the curve is, the higher insulation material provides. Another thing that we can see is that when we increase the thickness of the materials, the natural frequency will reduce, so shift on to the left, and the increasing the thickness provides a high insulation, so the curve goes down. The VC formulations combine the best of two worlds: insulation provided by rubber and dampening provided by cork. VC material have a high loss factor, resulting in a lower amplification at resonance. Shape factor is a key element to take in account when designing the VC solutions. The very low Poisson coefficients of VC materials, due to the cork structure, allows for a wide shape factor tolerance, resulting in more freedom to design robust and customized solutions.
Rui, how is exactly the calculation for the shape factor? What is important here?
Well, the shape factor is a ratio between the loaded area, total loaded area,
so the surface area,
divided by the perimeter surface area.
Okay, so that would give a number.
That will give a number that in VC materials, in cork and rubber materials, it's wider than typically materials of vibration control due to the cork. So typically we should design between 0.9 and 4 is the ideally shape factor we should obtain when designing these solutions.
And why is that so unique for the VC or vibration control materials in noise reduction compared to other alternatives?
The answer is easy, because it allows for customize almost any size. We are not dependent on offering a standard size, so we can customize according to the transformer design and not the other way around.
Okay, that's interesting. So it's a really more robust solution.
Yes, exactly. So going forward and looking at the 4 noise reduction strategies, this is a sequential approach where we should start applying the solutions near the source of noise, so near the core. So looking to the left, to the right, we should start implementing internal vibration pads, which will go under the active part. Then we should look at the core clamping mechanism. The idea is to decouple metal-to-metal connections from the active part to the tank, or to the top or to the sidewall. The third solution is the CLD, which stands for compressed layer damper, which is a solution for inside the tank wall. It's a sandwich inside the tank wall to provide stiffness to the wall. And finally, external vibration pads that are to be used outside of the transformer. Looking a little deeper on the vibration pad solution, we need to design the correct solution or the ideal solution. We need to have all these factors in account, namely the frequency. We need to know what's the frequency of the transformer, which in the case of transformers we know that will be 100 Hertz or above. We need to know the temperature at which the materials will be subject. We need to know the medium, if the materials are going to be used inside the transformer, immersed in oil, in which oil, outside of the transformer, indoors, outdoors. This information will provide will guide us to define the best material and the best solution. Center of gravity. And the center of gravity we need to know to distribute uniformly the pads in order to achieve a stable solution when positioning the pads. And finally, we need to know the mass, the weight of the equipment, the dimension, and the constraints we need to know how many support points exist, what's the available area, and with this information we can select the right material, the right dimension, the right number of pads, and the right position of pads to provide efficiently solution. It's also important to refer that this solution is under compression. So we are talking about pads that will be under compression, and it's very important to know that to take the max benefit of this solution, the pads should be compressed between 5 and 20% compression.
That's curious, Rui. Why between 5 and 20%? Is there a technical reason for that? I mean, or is it just a number?
No, there is science behind it. If it's 5 and 20 first, they are round numbers, so it's easier to identify those numbers. But it's important to say that 21% will work also, so we have a safety margin here. But the reason is below 5% material will be less, will be almost not compressed, so and above will be too stiff. And between these 5 and 20% we have a constant modulus. So the material has a linear behavior, so we can predict the behavior of the material and predict the expected output of the solution, providing insulation of the system.
Okay, perfect.
So to end up, we have 4 materials on the pad range. They are used for one particular situation. So we have VC2100, which can be used inside the transformer, immersed in oil. It's the only material that can be used inside the transformer, immersed in oil. We have VC7000, which is a high temperature resistance material typically used in dry transformers where high temperature resistance is needed. And then we have VC1047 and VC6400 used outside of transformer, being the VC6400 a premium one because it was designed to be in contact with the sunlight, with the rain, with excellent UV resistance.
Ray, a question regarding the application of these types of materials. Are we talking about what type of transformers are we talking about in terms of loading for these materials?
We can cover almost any size, any load, because we can design, and that's the reason of having a wider shape factor. We can design and determine lower area or a medium area for the pads to be used, but typically the high performance and these solutions are typically used in medium and large power transformers, where the benefits are more. So finally, let's see how to design a vibration pad solution using the NVD tool. So we are going to simulate live a few real case studies and design a few possible solutions. I will open the NVD software and I will go through all the steps to see the possible solutions and to see the final result, the output of each solution. The software was made to be very intuitive and user friendly. You will judge it, but let's go through and let's see how it works. So like I said, we are live. So this is the initial page of the tool, and by selecting the environment we are selecting the correct material. So there is no need to know which is the material that can be used inside the transformer, if it's VC2100, which it is, or another one. We just select the environment and the software will guide and will select the material. So coming back again, and we are going to present 3 case studies.
Sorry, Rick, can you just go back to the main menu? So each of these correspond to an application environment. The first one would be an oil-filled transformer.
Correct.
The second one would be on the outer part of the transformer, sitting in a field or in a city.
Correct.
The third one would be, can you help me here?
The third one will be used pads outside of transformer, but the transformer will be enclosed in a factory, in a in-house,
or an apartment or
will not
basement or something.
Will not
like
be
that.
subject to environment, rain, sun.
Okay. And the last one, of course, is self-explanatory. Okay. Thank you.
So coming back and starting with the case 1, we selected different case studies to show you real cases. We try to took out confidential information, but we need to put something for you to understand. So what we are looking is a transformer where the core weight has 48 tons, and we used internal pads. So this is the the information in, and you see also there are 7 legs with different sizes, with different width, and also with different length. You cannot see the length on this image, but so 7 legs with 3 different dimensions. So like we said, it was for internal contact. So let's select and do next. First one is easy. Then the mass, like I said, 48 tons, so 48,000 kilos. If you know the load, you can also select the load, but by inputting the mass, the software will calculate the load. The disturbing frequency, let's consider this one was 100 Hertz, and in doubt,
Can I just stop you there, Roy? 100 Hertz because of...
because the disturbing frequency of the transformer are the double of the electrical input. So
Okay, so the line frequency, so if it's 50 Hertz
will be
frequency, 100.
if it's
Okay.
60 will be 120, and so on. So the minimum disturbing frequency will be, even if we don't know it, 100 Hertz.
Which is the worst case
It's
scenario.
worst case scenario for our materials. And like we saw in the transmissibility curve, our materials at that frequency are well below are in the isolation region, well below. So if we know the service temperature, we can change. Let's keep it like that, or we can select for minus 20 to, let's keep the 100, but we have the option to select a different one. So let's say 110. So let's simulate like that and continue this line. Sorry, and you see the load was calculated based on the mass.
Oh, so it's giving us intermediate calculations.
Yes, so we can go through and we can check if the value makes sense or not. If we have input a wrong number, for instance, we can immediately identify if there is a mistake. So next step, we need to input the pad dimension. And to input the pad dimension, we have 2 options. One is using standard sizes, and we can see that the standard sizes are already defined. So we can select the standard sizes and go through. Or if we want to use a customized size because the legs of the transformer or the size we want to use are not listed on the standard sizes, we can input any value, and afterwards the software will tell us if the values are okay to proceed or not. In this first case, let's start with the standard size, and then we'll go do a second simulation using customized size. And for this first, let me just remind you that we were talking about 48 ton, where we are going to use internal pads with seven legs with different widths, different sizes. So we are going to select. We are going to select 300 length on the length of the pad by 200 by 40 millimeters, and automatically the software do the calculation taking in account the weight, the load, and the dimensions, and propose a value of number of pads that should be between 6 and 15 in this case.
Just stepping back, I see that Okay, there's no pad stress yet because you have not selected the number of pads.
Correct.
But you've predefined a thickness, or could I have selected something else?
No, the thickness is predefined because you don't have the option, in this case for instance, the 10 millimeter. Why? Because if you use those dimensions in 10 millimeter thickness, the shape factor will be outside of the limits. So will be outside of the linear region of the material.
But I could have selected 30 and 20 millimeters.
Sure.
Okay.
And you see with 40 the shape factor is 1.5, so within the range. If you change to 20, the shape factor change to 3, but still within the linear region, so 0.9 and 4.
Okay.
So let's use the 40 for a better efficiency of the performance of the material.
So the lower the shape factor, the more efficiency we're going to have.
Yes.
Okay.
So let's review. Sorry, like I said, we are live. It's live, gentlemen. It's live. Sorry for that. I just want you to remember the initial situation. So 3 different width, 7 legs. So let's see if this time we'll go. Okay, easier. So remember 7 legs. So using 6 doesn't make much sense. We have 2 options: 7 and 14. 7. You didn't saw the length, but the length of the legs are more than 900 millimeters. So we could opt to use 7 or 14, but in 900 millimeters using a length of 300, 1/3, this system will not be stable. So the best option will be using 14.
So you double up to get a surface area of length 600 against a seating length of 900.
Correct. And you
per leg.
Okay. And you see, when inputting the number of pads, the software will calculate pad stress and the shape factor. So in this case, the 5 to 20% compression typically represents 0.5 megapascal and 1.5 megapascal. So if we continue, and if the software allows us to come this way, is because all the values are within the limits defined. So if we continue, the output will be which is the material selected. In this case is VC2100, and this one is easier because it's the only one that can be used inside the transformer. We can see the value of transmissibility, the percentage of the insulation, the ratio between disturbing frequency and natural frequency, and the compression on the pad, 9%. We also we have more information, so we see the deflection in millimeters, we have the dynamic stiffness of the material, the TG of the material, the natural frequency, and the transmissibility, the resonance, so at 8, which is way below the 100. But we don't need to memorize these values because we can, clicking on report, we have a full report giving us all the input and the output that come out from this simulation.
Excuse me, in which format does this report generating? I mean, is it Word or?
It's a PDF, so
Okay.
you can print it, you can save it on your laptop, and you can email it afterwards. So it's and you have the information, the date where you did and who did the report.
So you are the administrator.
I am.
Okay. So this allows to have a track record of your engineering design solutions for various transformers. You can actually create a database of solutions for various types of transformer constructions.
Exactly. And like I said, there is not just one solution. You can simulate different solutions and kept all the information and see what fits best for the transformer.
Okay, so in looking at this information, I might guess that the most important section is the last one, where the material selection is, and here you can actually see the impact of using a vibration control solution in reducing noise in the transformer. That is through the isolation, correct? The 93% isolation?
Correct.
Okay.
The higher the value, the higher the insulation. So we are reducing 93% of the transmissibility input.
Okay. What would happen if I would use a different thickness, like say lower?
We can simulate. It's an easy question, but it's easy if so 93 was at 40 millimeter. So if we change to 20, we're gonna input again the 14 pads. So the only thing that changed was the shape factor. And if we continue, we see here the reduction on the insulation. So the insulation decrease by decreasing the thickness by 5%. So like I said in the beginning, when we increase the thickness, we are increasing the insulation. And we defined the 40 millimeter as the limit we can supply in a higher thickness, but the gain that we can obtain by using a higher thickness will not correspond to the gain in terms of insulation. So 40 millimeter will be the best performance thickness that we suggest.
Okay, so it's very dynamic. You can go back and forth and back and forth. So if I would say, okay, let's try a different size. I mean, maybe this size. I don't want the 300 by 200.
Okay, let's use a size that is not available on standard size. Let's do a customized size. So we need to start, and I'm gonna select some square pads, 150 by 150. And again, now you see where we have the 10 millimeter available, but I'm going to select again the 40. And you remember we have 7 legs, so we have options from 14 to 41. But we forgot, we didn't saw the 14 there, and we said 7 legs. Let's input 7. The software gives a warning to re-evaluate pad stress, correct pad dimensions or number of pads. So the software don't allow to go further if the parameters are not within the acceptable limits. So 7 doesn't work. The software already warned us that should be between 14 and 41. And we want again a stable solution. So any number of pads between 14 and 41 will work. The software will continue and will provide the output, but we need to have a stable solution. So instead of 14, we are going to use 21, multiples of 7. And meaning in each leg we're going to have 3 square pads of 150 millimeter. If we continue, we have again the solution, and you see with similar isolation, 93 was the first case, in this case 94% in isolation. So again, both solutions can be used. Typically the decision could be in terms of manufacturing process, which is the best size that allows the customer to use the pads. And so remember the first solution, and one possible the first case study, and one possible solution could be this one. So even if the legs have different sizes, we try as much as possible to design one pad size. It's easier. We don't need to remember that we have pad A goes to X place and pad B goes to Y place. So one size benefits in terms of manufacturing process on the customer. So going further and looking at a different example, this one is a transformer of 200 ton, and we are going to simulate external pads.
Okay, is there a seating area in this transformer, Rui, or is this a flat, or just to understand a little bit?
There is a seating area which is marked here. So this is the available area, will be these five areas.
Okay, and they're centered around the center of gravity.
Yeah, yes,
okay.
Yes. So in this case we have constraints, so we need to work around it. We need to, based on that, what will be the solutions that we can provide. Again, we are going to do 2 examples. This time was quicker. So let's go back on application menu and restart and do this new case study. So like I said, this is external for external use, and this one was to be used on an ambient environment. So we're gonna select the second one, and it was a 200 ton transformer. Again, 100 Hertz, and we can keep the service temperature, or we can change again if needed. So continue.
So actually, because it's an external solution, maybe we're around about 70 degrees on the upper limit, right?
Yeah.
And on the lower limit, maybe -40 for cold climates.
Okay, let's use the -40 to 70. Okay, continue. And in the first case, let's use a standard size, and let's use 500 by 250. using, you see now only 2 available thicknesses because of the shape factor, so the software will guide us.
Okay, so it's automatically calculating, so you don't have to calculate it yourself.
Correct,
Okay.
correct. So the software will somehow guide us through the input. So we can select 11, between 11 and 31 pads. Like we saw, we have 5 legs with 3 meters. So we're gonna the option will be for more stable solution to use 30 pads. We see then the calculation, pad stress, okay, shape factor, okay, we continue, and we have the final solution. Material VC6400, 94% isolation, 60.5% compression on material, and all the information that you can just print it out and save it if needed. But you don't want so many pads, and you want to use less pads because on the shop floor you don't want to have so many small pads. So you can use customize and use, for instance, 1250 by 250, sorry, 2 thicknesses available. We're going to use 40, and here the option again for higher stability will be to use 10, but it's always up to you when designing and see the best solution. We normally, as a guideline, what we say is that the higher the area, the more stable the transformer will be in terms of when working. So we prefer to work on the lower limit of the pad stress to have a more stable solution. And again, the solution was VC6400 with the same isolation percentage. So in terms of performance, either solution will work almost the same, will give almost the same performance. And we can then see, sorry.
Well, these are the live issues.
So one possible solution could be the second one. So using 10 pads with 1250 by 250. And finally, to have time for questions, one more case study. This one very fast, which again will be for internal 102 tons, so internal pads. In this we have also different pad size. Yeah, and okay, going back to the software is always easier. So we're gonna restart on application menu, and you see here we have the menu. When you click on application menu, goes for the initial screen where you can select the application environment, but you have other things here. You have the help with glossary of terms on the release date, and also if you have any doubts, the software will guide you to our website. Actually, you are not seeing, but it's opening in my laptop, so I'm blind now. Also, if you need to convert, by clicking on converter, there is a converter with with the units where also the calculator and then the exit is obvious.
So the whole program is in metric units, and so if you have inches or pounds, you just use the converter.
You need to convert and then input in the international measures, of course. So going back for the third case, so we were talking about internal pads, and just to finalize this solution, the weight was 102 tons. Let's skip the service for now. We need to define the frequency. In this case, we could use a customized solution, 500 by 150, which is the width of the supports, by 40 millimeters. And this case is a little bit more complex. I will not take too much time. I will just input 14, and you can see why I've selected 14 on the possible solution. So the pad stress within the limit, shape factor within the limit, and you have the report. So let's see if now I can go easily back. So one possible solution was to use, because the length of the legs are different, we are using a different solution using the same pad size but distributed along the legs.
Okay.
This could be another solution, adding another dimension to the transformer to increase the stability of the transformer.
Okay. Rui, I know that you could talk about this all day long and another day. So, and in order to comply to our webinar timing, I would ask you that we enter our questions and answers section of the webinar.
Here we are.
And we have identified some questions from the public that is have been so kind to put their questions on the chat. The first question that I would ask you is regarding the pad dimensions. So what I see, and that's what one of the questions that was made on the chat is, is it possible to have more than one pad dimension in a solution?
It is possible to have more than one pad dimension in solution, but not using this software. So this software is designed to use just one size dimension of the pads.
Okay. And the other question that has been put on by our viewers is, could you, in the case of a CLD solution, so a compressed layer dampener, could you use the NVD tool, this software, to dimension such a solution?
The answer is no. This software was designed to be used only with pad solutions, pads under compression. For CLD, we need to go with a different approach, not using this software.
Okay. Do we have another one from Stefano? And the question is it possible to estimate the reduction in sound power knowing the emission spectrum of the transformer?
Empirically, yes. The solutions, when using these internal pad solutions, empirically, and the data that we have says that impact of reduction in noise is between 2 to 4 dBs, depending on design, transformer design, and solution implemented.
Okay. We're also having quite a lot of activity now on the questions on the chat. Another one is, and it's from Charlie D44, double D44. So it's calling out to, when you have an internal pad, does it resist to the oil inside?
The answer is yes. The materials should be just one. So just one is VC2100. That one will resist the lifetime of the transformer. So yes, but must be VC2100 that goes inside of transformer.
Okay, thank you. And I think it's the last question, but I don't know because they keep rolling in. From Stefano Zunino, which is asking, are the pads useful also to reduce the vibrations, considering that they may be employed between the tank and the length support to reduce vibrations transmitted to the ground? So he's worried about vibrations to the surrounding.
Again, the answer is yes. The pads will reduce the vibration to the ground.
And that's based on the isolation performance that is presented in the solution.
Yes, correct.
Okay. So, thank you all. We have just reached, I think, just beyond our time limits for this webinar. It is with great pleasure that I have to thank the people that are viewing through the YouTube, and also the technical support that we have. Thank you, Rui.
Thank you, João.
Thank you, Diogo Marques and Tiago Lima. They have been an important asset in making this webinar a success. For the people watching us, if you have more questions or doubts, don't be shy, put them through. You have my email, which I presented previously. I will put Rui's email on the chat, and you can always ask, drop us an email. In any case, visit our website, leave us some type of a question, or give us some suggestions on the type of webinars that you'd like to see in the future regarding noise and vibration control, for example, compressed layer dampening design. Let us know.
To end up, this presentation content will be shared with you per email. The NVD tool is available for download on our website, but we are going to send the link along with the presentation content. So any doubt, please feel free to contact us, and we are available for any questions, any opportunities, any challenges. We are always open. So again, thank you for attending, and see you next time.
Yes, see you next time. Bye bye now.
Bye.
Bye.